Okay, class. Okay, welcome to the sixth lecture on multibody dynamics in the course Multibody Dynamics B. In this quarter, that's the final lecture. It's of course not the final lecture for the course, but for this quarter, this will be the last lecture. If we check, it's always good to check the schedule. If you go to Brightspace, I try to map out the dates together with the topics, and I keep a log file of what I did. And then you see here on Tuesday, March 27, that in 2 weeks there's no lecture. So this is the last lecture in the quarter, and then after the spring break we start again, or apparently on Thursday, at 26th of April. So we changed from the Tuesday to the Thursday. That's not completely correct. Actually, we changed from Thursday to Tuesday. Usually the course was always on Thursdays, and now Tuesdays is actually also breaking me up. It doesn't fit within my schedule very well, and I'm super happy that we now are back on the Thursday. Now a small insight on what's going to happen. In this quarter we had 5 homework assignments. In the next quarter we'll always also have 5 homework assignments. So in total there will be 10 homework assignments for the course. Lowest grade drops out. So your homework average is on the 9 best homework assignments. And then of course we have the digital exam, which is actually super easy if you did the homework. Most people then score a higher score on the digital exam than on the homework. And then the digital exam is your final grade. If your grade for the digital exam is less, then there's a 70%, 30% weighting for homework and digital. It's all on the website. Anyway, the main message is do the homework. Try to do it yourself, and the things you don't know, just ask help from others. And that's also how the work is graded. Okido. Yeah, last topic for this quarter is TMT method. I didn't think of the name. It's a very strange name, but people started to call it that method, and so it's stuck by that. But before we start with the TMT method, so this is the topic for today, the TMT method, we're going to do the quiz. In-class quiz number 6. Should the sound is off. Yeah. In the chat they say that the screen recorder is still good. Oh yeah, that's strange. What is that? Okay, let me fix that. Yeah, thank you. So this is the video capture device, right? Yeah. No, that's a video. My screen. This is my screen, right? So let's see. Let's see what we can do there. Crop. Manual to the window. No. Manual. And display 1. That doesn't work either, right? What is going on? This is my video thing, right? Okay. Okay. But now where is my... This is good, right? Audio, that's great. Audio is good, video. Video. That's okay, where did you go? Oh, on top. How did that go? Order. Move up. Yes. Okay, sorry for all these technicalities. I'm happy to hear from the back if everything is now okay. I guess it is, but yeah, let me go back. The recording, everything is running. So where were we? Oh yeah, the Kahoot. Okay, let's start a Kahoot. Okay. Well, 5 questions again. I just want to show the smiling faces in the audience. And I'm smiling too. So, yeah. So this question, although I immediately heard that people said, oh, it's about French. It's not about the French language. Pas du tout. Or no. So it is really that I want you to read that avertissement. I just want you to read it and try and understand it, because it's such an important part of the whole work. And maybe the most important. Who knows? Anyway, I think a pretty good score, 83. Okay. This went not so well last week, so I made a lookalike question. And please discuss. You should convince your neighbor that you have the right answer. Discussion is important because it's not about getting the right answer, but it's getting the answer right. Yeah. Okay. Yeah, I'm happy. Okay. Potential energy of a spring. Well, it should be easy, right? And again, convince your neighbor that you have the answer right. Yeah, very good. This is about this very simple load swing model. Yeah, discuss, please. Convince your neighbor. Very good. You are right. He's wrong, of course. No, I'm just kidding. Okay, remember what your answer was. I'll show the media again. I'll show the question. So definitely you need some feedback here. If I remember well, we discussed in the lecture, but it's also in the lecture notes, that you can find with the Lagrange method the equation of motion, and then you see a nice transformed mass matrix, and then the question is, does the system have a solution? And then we look at the determinant of the mass matrix, and lo and behold, we came to the conclusion that for all the configuration of alpha is 0 and pi and 2 pi and 3 pi, so hanging vertically down or vertically up, that there was no solution from these equations. And that is sort of strange to think, oh, what is going on? But apparently there's a velocity distribution in the system such that there is no kinetic energy. And that is, of course, an impossible thing. Then you have a motion which is not coupled to mass. Ergo, if you put forces there, you get infinite accelerations. So the correct answer is, of course, there's no kinetic energy connected to a mode of motion. So there are finite speeds, and the result is that the kinetic energy is 0. Yeah? Read the lecture notes. Okay, I think we move to the last question, right? Oh yeah, the TMT method. So the topic for today finds its origin in I think Google is not very helpful here. Okay. Yeah, please provide some feedback. That's always helpful. Oh, hey, we went a little bit down. Oh, we go up again. Yeah, keep up the good work. Oh, no, down. Oh, okay. Yeah, okay, thank you for participating. It was fun as always. What are we gonna do? Yeah, lecture. Let me check this. Looks good. Sound is okay. Air server, here we go, full screen. Okay, and then I'm not moving, but this is moving. Yeah. Here we go. So the method of today is a TMT method, and actually the three letters are, well, we will see at the end, because they resemble the formula we are deriving. It's about the transformation of the mass matrix. But actually what we are doing, we are again deriving equations of motion by in terms of generalized coordinates. That's our goal. And we're going to use the instruments which Lagrange used, but we're going to use them in a little different way. So our starting point again, again we use generalized coordinates. So you could say in the spirit of Lagrange. Okay, in the spirit of Lagrange. But we're going to do it a little bit different. And how we're going to do it? Well, let's first start again with the virtual power, because that's our powerful instrument in that sense. Virtual power, we have applied forces, we have all these mass terms, and we have the acceleration of the center of mass, and times virtual velocities. Of course, I and j are running from as many coordinates as you have, and those coordinates, let me are the positions of body 1, the position of body 2, and then you move on to the position of the B's body. And likewise with those forces, we had those Fx of 1, Fy of 1, M of 1, and you continue until you have the last torque. And then the mass matrix, Mij, is this nice diagonal matrix filled with M1, M1, I1, M2, M2, I2, etc. until you are at IB, the last one. So this really defines our whole system of rigid bodies. Now, nowhere in this equation do we have constraints, right? So this is just all the free floating bodies. But we want to look at our system. So either we add constraints. That's what we did in the past. We add constraints. And those are from the joints and maybe the impacts and all those kind of things to make up the system, or we use generalized coordinates. Because in picking those generalized coordinates, we actually already fulfill all the constraints. And as an example, if you take that double pendulum, one pendulum here, and then connected is the other one, two hinges, we have a support. Of course, we have in total n is 6. We have, because we have two bodies, x and y, but that's not so important. Center of mass you can indicate here. And by counting, we come to the conclusion with the 4 constraints that m is 4. That the result is that the degrees of freedom is in total 2. So if you pick generalized coordinates, you are smart to pick 2, because then you have almost a 1-to-1 mapping. You take 2 generalized coordinates and you have a configuration. It's not unique. Well, you try to find generalized coordinates which have a unique mapping. That's not always possible, but in this case it's super easy. What would you choose for generalized coordinates? Any ideas? What are nice ones for this double pendulum? I hear nothing. Absolute angles. Yeah, okay, so this angle, and that's alpha, and then this one, for instance, that's beta. Right? That's what you like. Okay. Well, that's a choice. If you want to know a motor between body 1 and 2, maybe you use a relative angle between body 1 and 2. That can also be useful. But it's your choice. I mean, it's as you like it. It's a Shakespearean approach. As you like it. So, in general, we can say with these generalized coordinates, we can say, okay, we have a mapping defined that we can find our center of mass coordinates just as a function of our generalized coordinates. And note, this is not energy. This is not kinetic energy. But I use the letter T because it's the transformation. So therefore it's the letter capital T, and it's a T with an index, so that differs really from the scalar T. Scalar T is kinetic energies. A T with an index is some transformation function. Okay, and if we define them well, then all the constraints are fulfilled. So now going back to our virtual power expression, then we can say, oh, apparently we can express our virtual velocities directly with this transformation function in terms of our independent virtual velocities for the generalized coordinates. That's super easy. If you know what the alpha dot and beta dot are, then and you know the configuration, you can calculate what the speeds are. Moreover, we also need in the expressions, of course, acceleration. So from the velocity expression, oh, that's too quick, sorry. From the velocity expression, which is the same, of course, as above here. That's not a nice comma. Q dot J. If we then differentiate again, then we find a nice expression for the accelerations. And isn't it beautiful that the tangent mapping, which is between this velocity and this velocity, is again, you have still the same tangent mapping between this acceleration and this acceleration. Plus, but then we end up with a whole bunch of KL, what we call convective terms. And again, if you want to exemplify these are in the order of alpha dot squared L and those kind of terms, centrifugal, all the accelerations which have to do with quadratic in the velocity, but also TV, 2v relative omega. That is, if you have some moving coordinate system, so generalized coordinates, some moving coordinate system, and within that moving coordinate system you have a relative velocity and the coordinate system is also rotating, then you have some magic acceleration which they call the Coriolis. Yeah, it's no magic acceleration, it's just a convective term. It has to do that you are a moving observer. It has to do that if you are on Earth, we are moving observers here, and you look at the sky and you look at the clouds, and you know where the high and the low pressure areas are, then the air is moving not in a straight line from high to low, but it's making all these curved, strange motions. But that's, of course, you're a moving observer, and you have centrifugal and Coriolis. Anyway, so those are the convective terms. Actually, and now we are in business because we just substitute the whole shebang in our virtual power expression, and we should have our equations of motion. Last thing we have to do is, if you introduce new coordinates, if we introduce new generalized coordinates, Qj, then you also have a new set of generalized forces, and we all like to donate them with capital Qj. Now, they are defined by the concept of power, so the definition of Qj is actually like this. Qj is by definition, I don't know how to write that, but by definition, I don't know, as such that the power is Qj Q dot J. If you know what mechanical power is, if you have your generalized coordinates, then the forces are in line such that they produce mechanical power. So if you have a distance, a horizontal distance, then the speed is the s dot, and then it's apparently some linear force. But now, if you define a generalized coordinates as the square of an angle, alpha squared, then that generalized force is probably a very strange thing. And so let's assume you have some angle alpha, let's say it's in radians, and that's your Qj, and then you say, well, no, I'm going to do a squared because I like that. For some reason, you like that as a generalized coordinate. Maybe because it always has to be positive or so, I don't know. Alpha is an angle, that's for sure. So that's a radian squared. So this is an angle. Then, by definition, this Newton meters, this Newton meter per second, this power should be your generalized force times your Q dot. And your Q dot in this case, if this is your Q, is just 2 alpha dot. Right? So now if you want to interpret this as a sort of a force, then the only way to interpret is that these are newtons, and these are meters per second. So this whole product is a force. So if you want to know what is Q, well, it's apparently the force divided by 2 alpha. Well, it's a scaling matter or so. That's when you choose your if you choose your generalized coordinates as non-direct physical ones. Okay, so intermezzo, that's not really important because we're not going to do that, but it shows that how do you define your generalized force? Well, with this definition, finally then the whole virtual power expression, let me repeat again, is let's start with this one, this Fij Mij x double dot j, that was what we had initially. But now we have some additional generalized coordinates, so we're going to add up this Qj delta q dot j for our generalized coordinates, because we have introduced new coordinates, we have introduced new forces, so there is more power into the system. Then we substitute, of course, for this guy our transformation, and for this guy also our accelerations. So first, then we continue. So our delta p star is is mij, and here we get for our x double dot our ti, well, k or whatever, doesn't matter. Q double dot k plus ti kl q dot k q dot l, bracket closed, times, and our virtual velocities are now according to this transformation, this ti, can I use a j? Yeah, j is okay. J delta q dot j plus our qj delta q dot j. And this, well, for dynamic equilibrium, we say this should be 0 for all those virtual velocities which are then non-zero. If that's the case, then the system is in dynamic equilibrium. That's our statement. Equilibrium. And dynamic equilibrium, meaning we get the equations of motion. So finally, and since this is for these arbitrary delta q dot j, we get j equations. And we have to reorder a little bit. Before we do that, just write all the terms out. So we have the fi minus this mij times it ti k q double dot k. So that's the first part of this guy. And then I do this times this. So I get minus mij ti kl q dot k q dot l. Always convective accelerations times mass. Then this whole stuff must be pre-multiplied with this Jacobian. That's like doing a sort of a projection. We project from a higher dimensional space on a lower dimensional space. We go from n, which in the double pendulum is dimension 6, to q, which is dimension 2. That will also be explained in the example. Oh no, s should be a plus, plus qj equals 0. So these are our equations. Now, of course, we have to reorder them a little bit, and we want to have mass times acceleration equals. So mass times acceleration. So we need this part, but note we have to pre-multiply or multiply with this. And yeah, in the index notation, the beauty is that you can flip the orders. You can say A, B, C, or C, B, D, B, A, or BCA or BAC. It doesn't matter how you write it. So, but some things are nicer than others, as with people. So yeah, that's life. So I start with this one, Tij, and then I do Mij. So that's good. The i's, they collapse. And now I have two j's, so that's not nice. So this should have been a j, right? That is not nice. So I want to get rid of that because that's making a total confusion. This one goes away. Yeah. So where was I? Well, make a k out of it. That's okay. Then we get a t, k, l, q double dot l. So that's our first part. So matrix. So maybe we put the brackets around it. And then equals. Well, what does it equal? Well, this is a super simple one. Just the generalized forces. And then what do we got? Well, plus, then we have this transformation times this guy. So Ti, the outcome is a j, so that's still correct. Tij times all these applied forces, Fi. That was the projection, projecting the forces on the lower dimensional space. And then again we have this remaining term, which is a minus, I guess, minus, yeah. Tij I need a little bit more space. Comma J, M I K T K L M Q dot L Q dot M. Yeah.
Could you elaborate on TIJ?
TIJ. What do you want me to say about it?
Well, it's a transformation matrix.
Yeah.
But from what to what?
Yeah. Okay, that's a good question. So, what was TIJ? Ah, here. Bingo. So we started, of course, with our functions, with cosines and sines and the CM positions, and then we take the derivative, and then we get a nice matrix. In our case, for the pendulum, it will be 6 by 2, and then it's just the transformation matrix of the velocities, in fact, and also the forces. Okay, so finally, this is our nice equation of motion. And this is also the reason why we call this method GMT method. Right? That's our origin. That's why people started to call it like that. I didn't do it. It's not my mistake. I'm innocent in this case. I would say it's just, in the spirit of Lagrange, it's virtual work. Lagrange didn't talk about power, so it's virtual work with D'Alembert forces and generalized coordinates. So those are the three ingredients, actually. So it's in the spirit of Lagrange. Lagrange, and then we say, what was it? Virtual work, Work. Second was D'Alembert forces first. D'Alembert forces. And the last one is, of course, the, go back. The last one is generalized coordinates. And so, if you throw that all in a baking pan and you stir and you cook it for, then you get your equation of motion. Yeah, Karan.
I was just wondering, this Q as well as F accounted for in the same equation. Are we accounting for the forces twice?
No, we are not counting for the forces twice. So, by definition, the Fi's are all the applied forces at the center of mass, and they have a direct duality with the center of mass coordinates, actually the velocities through power. And likewise, if you introduce new coordinates, you also need a new set of forces. Now, if you take as a coordinate an angle, which is like the orientation of the body, you say, oh yeah, that's the same as the alpha is then the same as the phi of the body. And that's where the confusion starts. And therefore, on purpose, I said, well, you can also take as generalized coordinates some angle squared. And then you see, oh yeah, apparently there is some magic force which in a product generate power. But we'll see in the example how that works. Okay, so these are our equations of motion. And of course, you can write them even in a more compact form, because if we use matrix vector notation, which is sort of nice also, because you work with MATLAB. By the way, yeah, I want to do a short poll, a quiz. Most of you work with MATLAB, so I'm not going to ask that. How many of you work with Python? Can I see hands? Well, as a computing tool. Yeah, Python. I saw one hand there, yeah. Don't be ashamed, just read Python, that's cool. Okay, yeah, because the university is moving from MATLAB to Python, as I understand. So I just wanted to see how far are we already in this curriculum. That's okay. And oh, another question. So you do your homework also with Python, or no, with MATLAB? Yeah, that's because of the TAs probably.
I know. I can use MATLAB better.
Yeah. Oh, even that. And are you using not?
Yes, I'm using MATLAB for the exercises.
Because?
Well, I don't know.
You don't know. Okay. Yeah. I thank you for that because it's helpful because the TAs are not so fluent in Python. So if they see Python code, they think, oh, probably correct. I have no idea. So, good. But we're going to move in the end. So. Okay. Yeah, so if we associate this Jacobian Tij with a matrix Ti, j, and this should be bold, and I'm not going to do this. So that's a matrix then, it's a bold, I'm not going to do it for the rest of the notes, but the Tij. And likewise, of course, this Mi, j is this matrix Mij, and the one index things are just vectors. That's super simple. Then we can write the equation like this: T transpose times M times T times Q double dot equals capital Q plus T transpose times F minus, I sometimes have a tendency to write this because these terms Gi is then what we call convective accelerations, Ti, Kl, Q dot K, Q dot L. Convective accelerations. I sort of like that definition, also because it is very confusing with a gravitational force, mg, of course. That's not so nice. So sometimes I call it h, but now for now, g. Okay. It makes the equation a little bit more compact, so this should also be a vector. But you can even move on by compacting even more, and this by saying, well, let's define a matrix M bar, and that is T transpose MT, right? And let's transpose generalized forces Q bar, and they are Q plus T transpose F minus mg. Or in words, what does it mean? Well, I have my CM mass matrix, and I'm going to transform it to some generalized mass matrix. It's still a mass matrix, and it's still symmetric. And my generalized forces, well, they are what the generalized forces, the applied ones are, plus the projection of the forces at the CM and the convective forces, convective inertial force. And then the conclusion is that we get M times Q double dot is Q bar. And that's all in the spirit of Newton. That's, of course, sum of the forces is mass times acceleration. And of course, I mean, that it should be like that, because that's all we are doing. We are cranking on very difficult machines where we finally, the only thing we are doing is forces mass times acceleration. Of course, we have the concept of a rigid body, so we have orientation, and it's a bit more extended. You could say Newton-Euler, but in the end, in a generalized sense, it's just force is mass times acceleration. A smart student in the room would say, well, what the heck, why do I need this very complex formula? Why do I need this complex formula? I mean, it's with a lot of indices, and it looks very complex, whereas I know a method that is far more simpler. And actually, the method goes like this. These are my equations of motion. It's super simple, he says. Why don't you do this? That's a lot simpler, right? Well, the equation, as I have written it down, looks very simple, but the amount of work you have to do, you will see in a week, is a lot more with the Lagrange equation. And let me try and explain how that is. If we look at the equation, well, you have to define kinetic energy and potential energy. And you can only define those two if you take your force equation and you integrate it. You go up one level to the energy. Because that's what kinetic and potential energy is. You take forces, you multiply them with either a small distance or a velocity times time, and then you integrate them. So I go up to the level of energy. But in the end, we want to have equations of motion. So then some mathematical machine, and then, yeah, the mathematical machine brings you down again to the level of forces. Now, this up and down, I know from experience as a human, is not very nice. If you run up the stairs and you think, oh no, I had to be down. Yeah, come on, guys. That's too much. That's too much work. So in the Lagrange method, you do too much work. It is elegant, but it's too much work. Okay. And humans are optimizers, so we want to do minimal set of work. Example. How are we doing on time? Break.
Why you say about the motor?
I have to stop something first, and then I'm with you. Stop the recording. Ja. Ja, dat gaan we zo doen. Hij was eerst.
Oh ja, natuurlijk.
En jij mag het via e-mail sturen, dan kan het gelijk veranderen.
Ja, zo ik wel.
Doe je dat?
Ja.
For the model you have to
When I
define.
say that's general coordinate, let us use affine beta. You say yeah, but if for example you have a motor, it's better to define a level design.
Oh, because if you buy the motor and you mount the motor between body 1 and body 2, then you mount the stator on body 1 and the rotor on body 2, and then it's a relative angle. Then the rotation. So you have to look at this kind of thing with a cylinder. If you have some kinematic or hydraulic cylinder between two parts, then you want to have the relative. Yeah. Okay, same trick.
Excuse me.
Yeah.
I have two small doubts. The first one is because I get that delta kinetic energy equals to work done. So basically, even if a ball hits the wall, the work done by the ball would be 0 if E is 1.
Yeah.
Yeah. Is that correct?
Should be correct.
Should be correct, right? Because the TA gave a remark that the velocity remains the same, but as it goes in the other direction, there should be a work done. But work done is a scalar thing.
No, so yeah, that's okay. TA said that because by definition, the E is 1 is that you say there is no energy loss. There is a force. Now, is that clear from the equations?
Not that much.
No, but it is a problem in the book.
Yeah.
So you can get bonus points if you say, oh, I really want to find out in the general case if that is true. You can start with a very small example, two balls hitting each other. If you then find the solution, and you can see does the solution zero anything. You can easily do it.
Yeah, it's actually zero.
I did it. And then for the general case, it can also be very easy.
Yeah, but that's what, because just before that, I checked it a lot, because even I had the same thing, because if the energy is getting reduced, if the velocity is getting reduced, the wall does the work.
Yeah.
If it's getting the velocity reduced to 0 and throwing it back, it should be double the work.
Yeah.
But then I checked it online, and I did a lot of research on that, and then I found out that delta K equals to work done, so it doesn't, you don't have to think about it now.
Yeah.
But then again, I just wanted to confirm with
No, and there's also a nice derivation in the book, or a problem. The solution is not there, the problem where they say, show that the energy loss is equal to 1/2, 1 minus A times rho, the impact velocity is in the rudder. And they say, oh well, if you put E is 1, then it's 0, so it should never be.
Yeah. Also, one more thing. When we say E equals 0, which is the classic case, does the thing which is getting an impact stick to it? Because there has been a lot of discussion with me and
not
my
sticking,
mates.
not
It's
sticking.
just relative velocity, right?
Yeah, it's
It goes
just that the
forward.
velocity is 0. But
Yeah, because
it could be that after the velocity is 0 there, but the acceleration can be non-zero.
Yeah.
So it can be leaving the wall again.
Yeah, and it doesn't mean, because that's what
It's not sticking.
I actually talked to Karan about it, and a lot of other people as well. We actually had a very big debate about it.
Oh, cool.
So those guys actually said it's a glue.
No, it's not a glue.
It's not a glue.
It's not a
That's
glue.
what I tried to tell them. Okay, yeah, if there are two cars and the E is 0, both would go straight ahead. But if at all one of the cars is just applied with the force, it'll leave the car.
Yes, exactly.
Yeah, so that's what that's why I just wanted to ask you once again, because if it were glue, all the things that I learned before was totally going to trap. That's it.
It's a bit difficult to come up with a problem where you have an impact
And then it's
zero
zero,
velocities, but then still the force says that it's leaving again directly after. That's maybe interesting to come up with an example that shows it.
Because in the last question, the impact question, when it hit the wall, so I told him that it will be like zero, and afterwards, if it's still able to move, because of the inertial forces, it'll slide down. But then we had a debate, they went their own way, I went my own way.
Very good. Good work. Thank you, George. Ja. Deze, dan moet ik nog wel zetten.
Het gaat over de emissies.
Oh ja, ja, ja.
Voor de Q's, de emissies K en L.
Ja.
Een aantal generatiecoördinaten.
Ja.
Als in, je gaat van elk afleiden, dus daarom je vermenigvuldigt ze met z'n allen.
Ja, dat is een mooie index over hier, ja. K en die L, wat het enige wat er vrij uitkomt is I, dus je mag hier ook fiets en auto zetten als index. Dat maakt niet uit wat je gebruikt. Dus daarom, dan soms zie ik, oh ja, ik moet een nieuwe indices gebruiken. Dan krijg ik K.
Dat is puur om te laten zien van, ze staan hier en ze komen daarna een stuk. Op zich
Je hebt alleen maar hier binnen nodig.
Ja,
en
ja.
verder niet.
Dit houdt dus de convector zoals
Allemaal ga ik gedaan. Dat gaan we straks in het voorbeeld. Ja.
dat is één wat niet helder te zien.
Nee, maar dat komt straks in het voorbeeld. Qua het algemeen en dan snap je toch niet hoe het werkt.
Ja,
Dan hebben we soms maar.
Yeah, I have a question about the configuration where C is in A, the origin.
Ja.
Because I heard a lot of answers, but what is exactly the thing there? I thought because C is exactly in A, you're kind of in a dead point, so essentially you just have a simple plane. The only thing that can happen is that it rotates around the origin.
Anyways, and I'm already here.
So it
Is
doesn't matter
that the
what.
only thing which can happen?
I think so. I heard people say that C can also move up vertically, but it doesn't make sense.
Yeah, so however, I saw last time when we watch a lecture, you can just like say everything on the right side. So you can see everyone's answers. In that case, you can like give a little more.
Well, this configuration
By the time we get out, where the ethics course.
But from the standardized can also be that this goes by
But it can be. No, because I agree that if there is like a slightest deviation between A and C, that some of the force necessary
You've never heard about force. You don't know forces.
slight deviation between A and C, it can be. But if it's like at the exact same point, then it's pretty good.
Now, if I'm in this direction, I want to go in this the things are rotating, that's called rotation 1, and they rotate in the same direction, right?
Ja, zeker. Ja, dus er was een relatie. Dat ik haar
This is plus, L, but I can also think of another one. And this is a positive and then both go up. So this is a positive bond. L minus this one. This is also you can find this positive
Also, you're gonna correct it.
You'll find these two puzzles. All the velocities which we feel usually when we have 5 on split. So you want to out of this null space, only one set of velocities. So what happens here? One is constrained that this try it. Well, try it. Do it. Go through the math. It's kind of weird. Therefore, you have to go through the math. You can reset your intuition.
We still have time for a short question.
Yeah. 10 minutes.
Okay, so I was wondering, you don't take the moments into account when you use Lagrange, because they're perfect. Well, they're not. With the generalized coordinates, they're not in the same direction, so you can neglect the work caused by the moment. Okay. Waarom neem je het rotatiemoment? Neem je dat mee via de moment of inertia?
Ja.
Ja, toch?
Ja.
Oké. Ik zocht naar bevestiging.
Oké, ja.
Oké. Dus via de moment of inertia neem je het rotatiemoment.
Ja. Ja. Want als je kinetische energie uitgaat, en de beker dan hier ook.
Ja. Oké.
Ja? Oké, gaan we weer verder.
Okay, let's. Of course, this was a nice general explanation how you get the equation of motion. The best way is, of course, well, how does it work? So we do a small example. And we take the same example, almost the same example as with the Lagrange method. But there's a small difference now. Okay, so we have this load swing thing. So there is this cart which can move back and forth, right? And then we had this distance S defined. I need a coordinate system according to Heike, x, y, and then an angle, phi. So this is the inertial system, and then the cart can move over a distance s, and then we had here this pendulum, and now I'm going to take some rigid body here. So it has a mass and a mass moment of inertia. And what else? Of course there's gravity working. So I can write here a force mg as gravity. Oh yeah, I need an extra coordinate, of course, for this angle. And I choose alpha. And then I have the distance of the cm to the support, and that distance is L. Okay, I identified this as point A and this as point B. And of course, the mass has a position and orientation, and I only have one body, so I'm not going to use index one. It's just x, y, and b, x, y, and phi. Now, the cm coordinates for this problem are xi, meaning x, y, and phi, and as generalized coordinates, I decided to take my qj's as s and alpha. And immediately connected with those, and of course with these also are forces, but for now I'm going to say are apparently this a force, because s is a distance, and here's some torque, m alpha. And these are of course action-reaction forces. So you could say, oh, apparently if this is s, then apparently on this point there is an applied force Fs, and it must be action-reaction, so against the environment there must also be a force Fs. Because a force is never alone. A force is never alone. It must be somewhere. So, and identically with the m alpha here, so we have an m alpha here, so apparently to the support there's also an m alpha as a reaction. Okay, where are we? Yeah, so we have defined all the stuff. Maybe it's good to also mention what the applied forces are, right? So then I do this, and then I move it a little bit down. Yeah, so the applied forces, oh, that was a small letter, small f, should be small f. Small are fx, fy, and some moment m at the cm. Okay, now the major thing we have to define is, or what the problem is, what is the coordinate transformation? Because we saw in the derivation of the equation of motion that the basic element there is that coordinate transformation and its derivatives. So we need to find out xi is this ti of qj. Or in physical terms for our system, you can say what is the position of this center of mass, or x equals, what is the x position? Well, that's s. Oh, no, we don't see s. Ooh, s, yeah. That's the horizontal distance plus this small distance, and that's this length times the sine of alpha. S plus L sine alpha. Then the vertical position, so measured from this point, is down, so that's minus, and it's L, and then it's the projection cosine alpha. And then the angle of the thing is, well, if we take the horizontal always as 0, then what is it? Or you could say it's just alpha. I mean, you can have any offset which you want, right? Or you can say, well, it's alpha minus pi over 2. Yeah, let's say that. Let's be correct. Is it pi over 2? Yeah, it's pi over 2. And then the horizontal phi is 0 is the horizontal thing. Yeah. What else? Okay. Now, what did we need for our equation of motion? So, for our TMT method, we have to look at the equation again. And if I do it by head, you had an Mij, a mass matrix that had to be transformed. Tik. And here also transformation TJL, Q double dot L. Right? This was the leading term. And then on the right hand side we had our applied forces. And then we had our transformation matrix Tik times Fi minus these Mij. And then these were the convective terms, and the convective terms were defined as Tjkl Q dot K Q dot L. So the only element we need actually to derive this equation of motion in terms from the transformation is we need this Jacobian and we need this expression. Those are the two things, and if we have them, then we just manipulate and add and subtract and so on. But actually, of course, this Jacobian has to do with the speed. So if we have our Qi, we're going to find out what are the speeds. Tij Q dot J. Or, forgetting about the formula, just take our positions here and differentiate them with respect to time. So, does that work? Copy, blah. Put them here, and then we're going to differentiate them. Oh, pen back, yeah, ddt. What do we get? X dot equals S dot. L is a constant, right? It's not a generalized coordinate. Their generalized coordinates can be confusing because usually it's x, y, and phi for coordinates, but for generalized coordinates you use strange symbols. So, but L is a constant, so L. And then cosine alpha dot. Y dot is, cosine is minus, so that goes away. Sine alpha dot. And then phi dot is alpha dot. So that is nicely those are the velocities. Or in other words, my Tij, my linear mapping is, well, that's not so clear. So first let's rewrite this as a linear set of equations. Is, and then we have a matrix, and then on the right hand side we only have two velocities, S dot and alpha dot. Oops. Oh, that was not so good. Alpha dot. It's ugly even. It's ugly. Alpha dot, and then just pulling out terms here and putting them in the matrix. So how many times do we have S dot? One time. And how many times alpha dot here? L cosine alpha. And for the Y dot we have, oh, we have no S dot. And then we have only L sine alpha. And for the phi dot, we have no s dot and we only have alpha dot. So this is now my Tij, right? So that's my Tij. And then what do we need more? Well, we need these terms. Well, these terms actually they come very naturally if you take again the speeds. So let's take the speeds. And then we differentiate those again. dt. What do we get? Oops. Well, we get x double dot equals s double dot. Now, you would first differentiate this, but I'm not going to do that. I first differentiate this with time, before we apply the chain rule. So plus L cosine alpha, alpha double dot. And then I have to differentiate this with respect to alpha and then times alpha dot. Cosine is minus sine, minus L, alpha dot squared, sine alpha. And then y double dot. Well, there is no s, so that's easy. And this I keep constant. I first do that one. So then I get L sine alpha, alpha double dot. And then I do the sine alpha, and it's a cosine, and it's a plus. So I get plus L alpha dot squared cosine alpha. And then finally phi double dot is alpha double dot. And now nicely in this expression you see two parts. You see this first part, which all has accelerations in it, and you see the second part, which has all, also accelerations, but with velocity squared. So if we look at the formula, it's of course x double dot I is T I j q double dot j, and that's of course this part, and we recognize immediately the same Jacobian. We get the 1 and the L cosine and the L sine, they're all there. Because the only thing I did, I put the second dot on the first dotted variables, right? From a practical sense of view. Okay, plus, and then here we have our convective terms, q dot k, q dot l, or in other words, let me rewrite them, gi being ti kl, q dot k, q dot l equals, well, it's a vector. Although you see a lot of indices, the two indices just go away, and the outcome to the outside you only have one, minus L alpha dot squared sine alpha, alpha dot squared cosine alpha, and a 0. I will come back later to this, but now, for now, we just go through the motion. We just follow the recipe. We have the Jacobian, we have the convective terms, we are now in business. We have now the equation of motion. And how do we get that? Well, we have to put everything together. So maybe let's first do the transformed mass matrix. So the Ti j m I k t k comma l. Meaning that that's actually the T transpose times M times T, and those things are more easily understood. So remember what the mass matrix was. That was simple, mass, mass, mass moment of inertia. The transformation matrix was a 1, and then I'm just looking at this, for instance, a 1, an L cosine alpha, and then a 0, an L sine alpha, and then a 0 and a 1. And I use the shorthand notation of this, and S alpha is sine alpha. And then in front of it we need to transpose of that thing. Well, that shouldn't be so hard. L sine alpha and then 0. Now if you want to multiply this stuff, then it's actually this thing times this thing, and here we have a scaling in between. Because this m scales this, and this m scales this, and this I scales this guy. So it's the first row times m, the second row times m, and the last row times I. So having known that, you can you forget about this thing and say, oh yeah, times m times m times I. So I can immediately multiply this. So it's a 1 times a 1 plus a lot of 0 times m. So the result is m. And then this one times this one, again m, L cosine alpha. Then this guy times this guy, that's again with an m, so that's m, L cosine alpha. And then this times this, oh, that's a lot, so that's L cosine squared, that's L sine squared, times m, plus I. So maybe I need a little bit more space. So that's m, L sine squared, plus cosine squared, plus I. Well, of course, everybody knows exactly that this is 1. So finally, then we come to the conclusion that this mass matrix is M, ML cosine alpha, ML cosine alpha, ML squared plus I. So that is our transformed mass matrix, or our M bar. So we now have the mass matrix. Then on the right hand side we have to generate some stuff. What was the right hand side? Do we remember? Yeah, we had those QJs. Well, they are obvious. And then plus our TIJs times our FI minus my FMIK GK LM. No, not LM. GK. Blah. Convective terms. Okay. No, these are simple. I'm not going to do those. So that's for later. So this times this times this. That's an interesting part. So let's write again this Jacobian. But remember, we need to transpose. So we need this guy, right? To transpose with this Jacobian. So undo. And this. So this guy we need. And then what else? Well, we need to multiply that with the applied forces. Now, what are the applied forces? Yeah, something with G. Eh? So Fx, Fy, M are, there was no horizontal force, there's minus mg, and there's no torque, right? Those are the applied forces at the center of mass. So that's a force 0 minus mg 0. Well, we can still draw a small picture. Why not? Here's the center of mass, and here we have mg. So apparently nothing in the horizontal, only in the vertical, and no torque at the CM. Then, so that is that guy. Then we have minus the mass matrix, MMI, times the convective terms. And those were, yeah, those were this guy, these guys. So duplicate, go down, down, down. Oh, that doesn't work. Oh. Almost right. Almost right, so... Oops, yep. So times these guys. And then we close the bracket. And of course, we plus our Fs and our M alpha, right? But that's obvious. Now let's calculate. So this times this is 0. And this times this is minus L minus mgl sine alpha. Oh, that sine is not nice. Sine alpha. Okay. Then we have to do this times this times this. Well, that's easy, because again, this is this diagonal matrix just scales the rows. So it's m times the first, m times the second, I times the last. There is no last is 0, so it's only m. So remember m. And then we have to take this times this times m, so we get a minus sign, and then here we have minus ml alpha dot squared sine alpha. And now this times this, we get a L cosine times L minus sine, and then, oh, hey, that's interesting. We get minus ml alpha dot squared cosine alpha sine alpha, and then plus ml alpha dot squared sine alpha cosine alpha, and then plus 0. Okay. Is that right? Cancels out, huh? Zut, zut. Those are gone. Oh. Okay, so finally, my conclusion is my Q bar, or J, I can put any next to it, are, what are they? Yeah. Well, you could say Fs, I'll take this one, then here's 0, and then minus minus becomes plus ml alpha dot squared sine alpha. These guys are gone. I have my m alpha, so I have my m alpha minus mgl sine alpha. Now to finalize the whole stuff, what do? Is we take our system, we go back to our system. I scaled down a lot in the process. Yeah. Anyway. We go back to our system, and let's draw it again, or let's take a copy from this. So what was the original system? This was the original system. Yeah, well, I'll redraw it again, doesn't matter. Sorry for the scaling up, this is not my intention. Let's get back to the normal scale. Yeah, so we had our system here. Hoopla. Here we had our Cm. This was alpha, and the distance here was s coordinate. Doesn't matter so much. Mass, inertia, and gravity. And then for this, because this should be L, by the way. So we know what the system is. Everything is there. For this, the equation of motions are apparently ml cosine alpha, ml cosine alpha, and I plus ml squared times s double dot alpha double dot equals fs. Yeah. Do you remember? Something with ml alpha dot squared. Yeah. Sine or cosine. Sine, because if the angle is 0, oh, I used the other notation. Let me go back to the notation. Now, is it plus or minus? Plus? Yeah. Is it on physical intuition or because you checked? I was trying to do physics. I will show you in a second. Okay, then the second equation was m alpha. And there was a minus somewhere. Minus, and then mg. Oh yeah, L, of course, because it should be a torque. So mg L sine alpha. Okay. Now let's interpret our result. Well, first of all, the amount of work. You can compare it to Lagrange, and clearly we have done less. You will see. I think it's even the homework assignment, not on this problem, but on another problem. But I'll promise you it's less. Because the only thing we needed was this Jacobian of the transformation matrix plus the convective terms, and then we were done. we didn't have to go through, well, first do the speeds, then take the squares and add them all up, and then you have kinetic energy, and then when you have kinetic energy, oh, you differentiate them again to the speeds, and then when you have them, you have to differentiate them to time, but differentiating to time means differentiating to the coordinates, and then the coordinates to speed. So there's a lot of work going on where you say, oh, do I have to do all this work? And the answer is no. The only work you need is Jacobian, convective terms, and you're done. Having said that, let's look at the entries. What do we see? So what do we feel if we only accelerate linearly? So meaning the pendulum. Oh, that's not what I meant. I only wanted the pendulum to move. So the pendulum is not swinging. So the alpha double dot is not accelerating. Then the force here is just mass times acceleration. So that complies. If this thing is just moving. The other one, this one, we can also easily identify if it's correct. So that is just about rotation, about swinging. So you keep this constant, and then you have a swinger here with an alpha double dot and a torque, and apparently around this point of rotation. So the torque we feel there is apparently, yeah, the mass moment of inertia here, which is the mass moment of inertia here plus mass times distance squared. So that's I plus ml squared. Yeah, correct. So these terms are correct. These ones are a bit more difficult. So then you have to do in your mind the experiment. There is no linear acceleration, but there is an angular acceleration. So it's accelerating. And what force keeps this not accelerating? That's a bit more tricky. But apparently it's ml cosine alpha. So if alpha is 0, then force is maximum. And apparently if the alpha is 90 degrees. Let's look at the right hand side. Well, of course we have these forces. Two terms. Let's first look at this one. So the torque we feel here. Well, gravity, and maybe I can put the force here, mg. So gravity is a force down. This is length L. The torque about this is this distance times mg. So that is clearly L sine alpha. That's this distance times the force mg is the torque about this point. So I agree, and it's a minus sign because this is plus and the torque is this way. Totally clear. Now this one. So what is that? Alpha dot squared. Well, as I said, these are like centrifugal terms, these convective terms. So, well, let's draw it in the figure. So if we have this pendulum here, and it's in some configuration with the mass here, of course it's an extended body, but, and then there's an angular velocity here, then we know that the angular acceleration, if I draw that in the figure, it's pointing like this, right? This. I'm still busy with drawing an acceleration. So you're probably right, but let's see. So here we have an acceleration, the centrifugal acceleration, and the arrow indicates the vector quantity, and the magnitude is alpha dot squared times L. That's inward. Now, and in the spirit of D'Alembert, we can then say, oh, but that is, according to D'Alembert, that's what we did all the time, that's a force, and then the force is in the other direction, right? So apparently there's a force like this, and that force is equal to, what is it equal to? Mass alpha dot squared times L. That's the D'Alembert force. Maybe I put an inertia or so on it. That's inertia force. It was minus, and I put the minus because I flipped it. Okay, and what are we looking at? We are looking at a torque equation. Well, in the torque equation there is no alpha dot squared. You see why? Because the force is linear with the length of the thing, so there is no torque. It can never generate a torque. There is no torque. But now, apparently in the linear direction, we have a component. Yeah, that's true. You can decompose this force in two components, in a horizontal one and a vertical one. Well, the vertical one is what the support takes away. That's a constraint. And the horizontal one, yeah, that's a free force. So that's moving the thing. And that's this thing times sine alpha. So yeah, I'm sorry, it's sine alpha. By physical insight. One step back. When I said, well, this force disappears. Because it's collinear, of course, with this length. So it doesn't contribute to torque. That's a physical explanation. Let's go to the math. Because in the math we see that happen. And where do we see that happen? We see it happen here. Here we have the convective accelerations. That's exactly how I've drawn them in the figure. Remember? Acceleration pointing in that direction. And it was alpha dot squared times L. That's exactly this thing. In the x direction minus, and in the y plus, and no. So this acceleration, and then this projects this acceleration on our degrees of freedom. That's the whole thing where I try to say it's a projection method. It's the transformation projects our equation of motion on the generalized coordinates. And how does the projection go? Well, 1 times this, we only get this horizontal component of the force. We had a force in two directions. We only need the horizontal component. And this projection is a bit more complex, but that means along the direction of the pendulum. And along the direction of the pendulum times this, the result is 0. So it projects on that. So that is the physical explanation of our equation of motion. Finally, can we always solve these equations? Is there always a solution? Remember the quiz question with the pendulum. So, is there always a solution? Can we always solve for alpha double dot and s double dot? That is the question. Well, how do we check that? Yeah, the determinant of the matrix, the leading matrix. So in this case we take the determinant of this m bar. This is the m bar matrix. And that comes down to m times I plus ml squared minus m squared L squared cosine squared alpha. Or again you can write m squared L squared 1 minus cosine squared alpha, but you get another term plus mi. And yes, if alpha, so this one is of course 0 for alpha is, what is it, pi over 2 or something like that. Oh yeah, but the whole thing, not the 1 minus, it should be 1, right? Yeah, sorry. 0 plus k pi. This is, that's 1 minus 1. So then this thing is 0. So that's for alpha 0 plus pi was k pi. But this will never be 0. Yeah, unless you make the mass moment of inertia 0. Yeah, that was the previous problem. Or you take 0 mass, but then you only have inertia and no mass. And well, you should patent that if you can find it. So ergo, yes, you can always find a solution to these equations. And that finalizes the lecture for today. Please do your homework assignment. You have a week again for that to do. Hand it in, and I see you in quarter 4.